Good morning, my name is John Cowart. I'm an instructor here at Lincoln Tech. Today we're going to talk about basic subcooling, superheat, de-superheat, and compression ratio and how it affects the system. So here I have an outline drawn of the system, and basically you can see on here we have different parts. So we'll start off with here and looking at a few things. If we go to A right here, this is going to be our evaporator. So we'll say that as A is evaporator. A equals evaporator. How do I know that's the evaporator? Well, I can usually tell that by this gauge here is my compound gauge, and it's connected to the low side of the system. The evaporator is on the low side of the system, so therefore that must be the evaporator to get that lower pressure. And I've got a temperature probe right here on the line. So this would be my suction line. So let's go ahead and do B here. B is our suction line. All right. So if that's my suction line right here, then this 50 degrees must be my suction line temperature. So I'm going to put SLT up here for suction line temperature. Now let's look, we got A, B. Let's go ahead and do C. C would be our compound gauge. That is a gauge on our gauge manifold sets that reads above and below atmospheric pressure. So compound gauge would be C. D would be the opposite side of our manifold gauge set, the red gauge, which would be our head pressure or high pressure gauge. We'll just say high pressure gauge. We come down here, we got E now. E is going to be our compressor. In the refrigeration cycle, the compressor is actually the heart of the system. So E would be our compressor. F is going to be our discharge line. Discharge line comes out of the compressor and goes to the condenser. So F will be discharge line. G is our next one. From the discharge line, we go down and we run into the condenser. The condenser is where the heat is rejected, as the evaporator is where the heat is absorbed. Condenser is usually on the outside of the unit, so the heat can be rejected to a place that it makes no difference. So like, for instance, like on your house, you're going to have a condensing unit on the outside. You'll have your evaporator somewhere on the inside of the house. This is so that the heat absorbed here can be rejected here. H. H right here is going to be an expansion line. Expansion line comes out of the metering device. Let's go ahead and put that there, expansion line. I is going to be our metering device itself. So the high pressure liquid comes here, goes through this metering device, and it changes it to a low pressure liquid. So we got high temperature, high pressure liquid. We've got low pressure, low temperature liquid on this side of the system. Last but not least, we got J. J is going to be our liquid line. Liquid line. So basically in this system, the flow of the system is going like this. The compressor raises the pressure of the gas to a high temperature, high pressure vapor. It discharges through your discharge line to your condenser. The vapor is condensed into liquid. This is where the greatest amount of heat is rejected. The liquid goes down here, high pressure, high temp, and the liquid line goes through the metering device, which causes a pressure drop. The pressure drop causes some flash right here. We call that flash gas. The low pressure, low temperature liquid goes through here into the evaporator. With the heat coming across the evaporator from usually a blower motor, the heat inside your home and a refrigerator, what have you, it boils the liquid off back into a low pressure, low temperature vapor and sends it back around this way to be recompressed so it can go reject the heat outside again. All right, so we talked about this was our suction line temperature. This is going to be the coldest line on the unit. You can always tell the suction line because it's the coldest line there is. The hottest temperature we have is 160 degrees. That's going to always be our discharge line. So discharge line temp is DLT. Down here we've got 105. 105 down here is pointing to our liquid line. That is going to be our liquid line temperature. Now that we've identified everything, we always make sure we know what kind of refrigerant we're dealing with. So we'll know how to use our PT chart. So now then what I want to do is I want to take my PT chart out. Now that I've identified everything, I understand the flow. Now I want to figure out what's going on up here, what my gauges are actually telling me. So we're going to go to our Danfoss PT chart, refrigerant slider. We're going to go to R22. The first thing we're going to do is we're going to change this pressure into a temperature. So we're going to put in, and I just like to press on it so I can manually enter it, 260. That's going to give us 120 degrees Fahrenheit. So at this pressure, the temperature of the refrigerant is 120 degrees Fahrenheit. And that's what we call our SRT high. That stands for saturated refrigerant temperature on the high side of the system. Go ahead and put PSIG down here and PSIG down here. All right, now that we know what our SRT high is, we can go in and let's get this other pressure converted. So we're going to go back in, we're going to put in 68 PSIG, and that's going to give us 39.61. Well, let's go ahead and just say 40 PSIG. Or 40 degrees, I'm sorry. 40 degrees Fahrenheit, and that's going to be our SRT low. That's going to be the saturated refrigerant temperature on the low side. Now what this corresponds to is this is the pressure and the temperature at where this is changing state in the condenser. This is the pressure, this is the temperature where the state of change of state takes place in the evaporator. So now we're going to calculate. We've got everything up, we know all our numbers. Now we can plug and play on some formulas and figure out what this system is doing. So I'm going to go over here, I'm going to look for superheat first. What is superheat? Superheat is heat added to a vapor after it's already boiled off. So basically once a liquid boils off to a vapor, if I add any more heat to that vapor, that is considered superheat. So superheat is how do we find that? We follow a formula. Formula for superheat is suction line temperature minus our SRT low. So our suction line temperature is 50. Our SRT low is going to be 40 degrees. So we can't subtract temperatures from pressures. Everything has to be in a temperature for us to be able to subtract it. So that's going to give us 10 degrees of superheat. 10 degrees of superheat. Now, average superheat is going to be anywhere between 8 to 12 degrees Fahrenheit. So that's average what you're looking for on superheat. So you're asking, well, why do I need to know that? What is the purpose of me knowing superheat? Purpose of knowing superheat is when you start charging basically units up and they're operating, that's basically how much heat we're picking up in the evaporator and it's going out to the condenser to be rejected. So that is our superheat. The next thing we're going to do is subcool. Subcool. What is subcool? Subcool is after this condenses into a liquid. Subcool means how many degrees the liquid is. So anytime we have subcool, we've taken away so much sensible heat to this that it wants to stay a liquid. It doesn't want to boil again to a vapor, not right away. So subcool. This also helps us understand when we're charging a unit if we've got it charged right. So this is all part of what you would do when you go out on a service call and check things out on a unit. So subcool, how do we get that? It's going to be SRT high minus the liquid line temperature. So you would actually have your gauges on this, and then you'd have a thermometer on these places here to find out what these temperatures are. And that's what you'll be doing hands-on when we're able to get back in school. So SRT high we said was 120. Liquid line temperature we said was 105. 120 minus 105 should give us 115, I believe. Or 15, I'm sorry, not 115. 15 degrees of subcool. What's the average subcool we're looking for? We're looking for anywhere between 10 to 15 degrees of subcool when we're looking at a system. So right now, we're basically in the pipe. We're 10 here. We're in between those two numbers. We're 15 here. We're just on the outer edge of that. So right now, this looks like this unit is performing correctly. By the way, I can tell it also acts like it's charged okay. Okay, the next thing I'm going to talk about is de-superheat. What is de-superheat? Well, when we come out of our discharge line of the compressor, which is high temp, high pressure, we come down this line. We're 160 there. So as soon as we come out here, we're going to start dropping temperature. And as it gets closer into the condenser coil, the air across it's going to drop the temperature anymore and be able to basically change state of the refrigerant from a vapor to a liquid. So we're going to de-superheat. So I want to see how much heat we're losing before it changed state. So DLT is de-superheat. So let's do that. De-superheat equals discharge line temperature plus 50 minus the SRT high. So let's see what we got on the de-superheat. So discharge line temperature is 160 plus 50. I believe that's 210 if I'm not mistaken. It's Friday, so brain doesn't work as fast, so I'm always going to back myself up with my calculator. So we said right here we got 160 plus 50, 210. 210 right there. That does not mean divide. I'm just crossing it off so you don't get confused with it. All right, now we're going to subtract 120, which is the SRT high. And that's going to let us know how much heat we're losing from these points right here. So let's do that. 210 minus 120, basically 90 degrees Fahrenheit. So our de-superheat, so the point it comes out right here to the first few passes of this condenser, getting to where it's going to start to condense, we're losing 90 degrees in there. Also, that can tell you how your compressor is performing. If the discharge line temperature is way high, then you may have a problem with the compressor. But for this point, we just want to learn how to calculate these things. Last but not least on here, we've got what we call compression ratio. Compression ratio is basically how much compression we're getting in it. Any of you guys that have worked on cars, you hear somebody say, oh, yeah, my engine's got 10-to-1 compression, 8-to-1 compression. So for every stroke of this compressor, it compresses things down, the gas in there, and that's what raises the pressure and the temperature when it comes out through the discharge line. So we're going to do a compression ratio. Great thing about compression ratios at this point, we don't have to change much of anything, but we're going to be working with the pressures. So, compression ratio. Compression ratio equals, now a couple of things. This is gauge pressure. This is gauge pressure, PSIG. We have to turn that gauge pressure into what they call PSIA, absolute. So to do that, we're simply going to do this. So it's going to be something to the matter of, we got 260, 260 PSIG, and we've got 68 PSIG. Well, we're going to add 15 to both of those, and then we're going to divide again. Reason we do that is pressure at sea level is 14.7. If we add that to a PSIG, that's atmospheric pressure, 14.7. If we add that to a PSIG, we'll become a PSIA, an absolute pressure. So 14.7 is what the book says, but I always do 15. That way you don't have that decimal point. It's not going to make that big a difference, and you're still going to know what you're doing. So let's add this up and divide right quick. $260 plus 15 equals $275. 68 plus 15 equals 83. Now let's divide those together. 275 divided by 83 equals 3.31325301. Stop after the first two. So we can say the compression ratio here for this system is going to be 3.32 to 1. That means the compression stroke in the compressor is compressing that gas down to the cylinder volume 3.321 times. So it's like you got that much in there, 3 times the cylinder volume in that one stroke. Now, compression ratios can tell you a different thing. High compression ratios could be 8 to 10 to 1. Low compression ratios could be 2, 1 to 0. That can tell you how your compressor is functioning inside this. So always keep an eye on that. All of this plays together. Everything is like it's kind of like a human body. It's a heartbeat. It's blood pressure. It's everything in here. Everything relates to each other, and this is how a system actually performs. So this is how you find all these things. And usually in a one-on-one class, we do a little bit of hands-on when we do this. So I like hook the gauges up to the machines and things like that, and you can actually come and read the pressures, things of that nature. But since we got this coronavirus going on, we got to do it this way. So when you come in, when we actually do get to the hands-on, this is what you're going to be doing, but you're going to be able to do it live. But you need to understand how something flows. So remember, coldest temperature in the system would be the suction line. That tells you where the suction line is. Hottest temperature is the discharge line. So you know if that's the hottest temperature that you're going to be flowing this way. 105, the middle temperature, that's always going to be the liquid line temperature. Comes back around and goes. And it just goes over and over again and keeps running until the thermostat tells us that we're satisfied and the unit can shut off. Just like your AC at your house, your refrigerator, what have you. Thank you very much. I hope this video helps you. I'll be so glad when we get back in the classroom and do some of this hands-on. Take care.